Thank you, Zach, and thank you to the organizer for inviting me today. I hope you hear me well, and I don't know if you see me on the screen, but you should certainly see the slides. Okay, so I was tasked to give this talk on overviewing the field of numerical relativity, and this was a big task because there is a lot that's been done in this field. So I hope that I can give you at least some of the key insight and at least my perspective on those insights and challenges and prospects for the future about this field. I will start with, let's see, I will start with the role of numerical relativity in the first observation of gravitational wave from a binary black hole merger. Numerical relativity, for those of you who have been around in this field for quite a while, you know that numerical relativity has been historically tied to the field of gravitational wave observations. And this was, in a way, a culminating event we had was with the observation of the first binary black hole merger and their gravitational wave, GB150914, where you can see how the numerical relativity calculation and the numerical relativity calculation also that were used to calibrate analytical relativity waveform model match the data fairly well. So there has been a lot of work behind this field for a number of years, and for a number of years it has been very difficult to solve the Einstein's equations on a computer. Certainly, we are not. It's not like it is now. In fact, there was this bet from Kip Thorne, who you know won the Nobel Prize in 2015, where he had bet that numerical relativists. I will read you the bet actually. I have bet these numerical relativists that gravitational wave will be detected from black hole collision before their computation are sophisticated enough to simulate them. I expect to win, but I hope to lose because the simulation results are crucial to interpreting the observation of gravitational waves. And finally, I would say that the problem was solved a little bit actually 10 years before the gravitational waves that were detected. And so in a way, we won the bet, numerical relativity won the bet. And Kip could could have a sigh of relief because he actually was able to lose the bet, but also win it because obviously gravitational waves were observed. So today, the world of gravitational waves and binary black hole and binary neutron star include nearly 100 of sources. And that's really amazing. You can see here the various masses, both the masses of the two components and the mass of the merger remnant on this beautiful map that was produced for the LIGO scientific collaboration. So as Zach mentioned, numerical relativity is interested in opening a window into the universe because obviously we are modeling objects, compatible objects in strong field gravity, and often there is also matter around. So we are talking about also modeling binary neutron star, black hole and neutron stars systems, and possibly accreting binary black hole. Those can also produce very powerful electromagnetic signal and high energy particles. So in addition to gravitational waves. So there is a great potential for contributing to the observations of not just the current facility, but future astronomy facility in the future. And there are many that are coming up very soon. So it's fairly important, like in the first LIGO observation that I've shown to you, it's fairly important to be able to do these theory and computational astrophysical models in order to interpret the observations. And so I would say the fun for numerical relativity has just started because these observations are going to become more and more, and our models are going to tell us much about what's happening in the universe. In the future is very bright. And so if you are a graduate student or even a postdoc, we know that we're going to have many more gravitational wave observations in the future, because we have third generation gravitational wave detectors that are being planned, and LISA, space mission that will be flown. And we are going to be able to do really precision astronomy with that. We are going to have a much greater sensitivity. In fact, the signal to noise ratio is of the order of 1,000 or greater, and we'll be able actually to observe with this new observatory all the black holes in the universe, essentially, and neutron stars across cosmic time. This is pretty impressive. So we really have a lot of work ahead of us to do. And not only that, there seems to be also a lot of interest in combining the observation from third generation gravitational detectors and LISA. So you can do, for example, follow up this binary from the early spiral down to merger for their entire history. And it will allow us not only to obviously do a census of all these black holes and binary neutron stars, but also learn a lot about their origin, where they're coming from. So there's a lot that we are going to be able to do, and we're going to be able to look at the physics of extreme dense matter with gravitational waves, and also multi-messenger astronomy observation. Do learn a lot about nuclear physics, do precision tests of general relativity. So it's really exciting. In these plots, you can see the sensitivity of these detectors, the various detectors, and that they can reach that far really into the universe. So I will first review a little bit the current status of numerical relativity concerning the binary black hole waveforms calculations, and then I'll talk a little bit about the future. Now, numerical relativity has been used to calculate waveform models because waveforms are essential to inform the source parameters, the masses, black hole, effective spins, distance, or the neutron star radius if we're talking about binary neutron star and the equation of matter. Numerical relativity has been used quite a bit in the gravitational wave community to build hybridized phenomenological model and to calibrate effective one-body model, for example. It's also used to build surrogate model, or you would say surrogate models are interpolated actually from numerical relativity simulation. So we have a number of these waveforms constructed through these methods today. There's templates that are also being built using directly numerical relativity calculation. So today we have kind of 1,000 of such calculation templates. So a variety of spins, masses, eccentricity, and waveform length. Mostly focus on binary black hole mergers, but they seems to be fairly sufficient to do the science that we can do today with the observations. So in the plots that I have here is one of the simulation that shows, for example, that a numerical relativity calculation of a source like GB17 or 104, this is a processing binary, is 10 times better than actually the residual noise in the detector. So today we're doing pretty good in terms of using our calculation to interpret the results. We have a lot of catalogs out there. I'm showing here just a few of them. This is the RIT waveform catalog that can include also now eccentric waveforms. The SSX catalogs, I think Geoffrey will be talking a little, I don't know if he's going to talk about catalogs, but he's certainly at the meeting, so you can ask him more details about this. And these are really, contains a lot of waveforms, but they're still, you see, very challenging to complete, especially in the regions of unequal masses, very high mass ratio, okay? And so we have really to continue to produce these gravitational waveforms, even if we're doing fine right now to interpret the current data, we still need to cover the parameter space. And if we want to have longer waveform, for example, we have still a relatively little coverage at 20 Hertz and lower. So we have to have longer waveforms. Okay, so are we ready for the next generation science though? Well, the waveform accuracy, length, and parameter space coverage really need to be improved, right, for the future observations, because the signal to noise ratio will be so much greater. So the errors in the current numerical relativity waveforms, it has been shown in this paper by Pura and Hester, have to be really decreased by an order of magnitude. Errors in the semi-analytical model will be worse because they need to be actually decreased even further. But we have the lesson here is that we really have to improve our model if we want to be able to do the science that these gravitational wave detector will bring to us. So, and similar, this is going to be for LISA. We're going to also have to improve. We'll need longer waveforms, so not just a few cycles. We'll have to have much longer waveforms, so the codes need to become much more efficient, not just accurate, but much more efficient. We must explore the parameter space and also include not just high mass ratio and spin, but start looking at eccentric binary. Why eccentric binaries? But if you look at the latest, some of the latest research in this field, I'm quoting here, for example, a paper from Samsing, Nature, Joan Samsing, and he looked at the AGN disk environments where you can find mergers, BBH mergers that have an eccentricity that exceed 0.5. This was done for using post-Newtonian calculations, but one may think that if you have an eccentricity of greater than 0.5 at 10 Hertz, then there will be large residual eccentricity also possibly lasting at merger. And so this is very exciting also because these black holes would be spinning and they would display also orbit spin tilt. So these are fairly complex simulation and still very challenging simulation to do today. There are catalogs, as I mentioned, showing those simulations. For example, here, there is a paper by Gayatri on Nature Astronomy that showed that GV 1905-21 was fairly consistent with a highly eccentric merger at 90% credible level. So we really need to take a look at this and look at how we can model the system better. Okay. Well, we're talking about waveform and as we extract those waveforms in numerical activity, we usually do extract at a finite radius, and we use extrapolation methods to infer the waveform far away where the observer is located. We use perturbative expansion to higher order, perturbative in 1/r, and extrapolation to infinity. These methods still produce some errors, and so these needs to be improved. Cauchy characteristic waveform extraction in principle should be much better in improving the errors at infinity, but and could also resolve some of the big questions still out there. Is there a memory effect in those waveforms? And so, but in order to answer this question, we need to really push this research and understand, or this whether there is a memory effect or not, and it has to, in order to do this, one has to have a careful treatment of the BMS frame at future neural infinity, for example, because there is this super translation freedom. So I'm not going to say much more on this, but keep in mind that this is also an area where you can contribute greatly. Okay, so about codes today. We have a lot of codes today. So this is just a list that I took from this NOMAS paper. And I haven't counted. I hope I don't miss this. This was as much as the last that I grabbed in April. As you can see, there's quite a bit of numerical relativity code. So would you want to write another one? Yeah, sure, go ahead. But there are many of these that have been already developed. Some of them are open source, some of them are not open source, but we have a great deal of codes today. So that's great. So how do most of these codes work? Well, not all of them work this way, but I'm going to describe how most of these codes work. They are based on the so-called Cauchy problem. And so where you split the space-time into spatial foliations, then the equations become either constraints equation, the elliptical equation, and evolution hyperbolic equations. In order then to solve the problem, you first solve the constraints equations, and that is means that you construct initial data. Okay, for binary black hole, for example, the problem has been largely solved. Up to very high spins, up to 0.99. So we're able to solve the constraints with fairly high degree accuracy in this case. For binary neutron there's a little bit more work to be done, but for binary black hole, this problem is well under control. For the time evolution, we use the BSSN NOC equation or other formulation, similar formulation. There are a set of hyperbolic PDEs which are complemented by a suitable gauge condition, for example, the moving puncture. And then we do this extraction of the waveform that I mentioned before, and that's been done with either higher order extrapolation or CC. For binary neutron star and black hole neutron star simulation, these are slightly more complex, but I hope that the next talks are going to address a little bit this question in this workshop. So there is a lot of history in numerical relativity, and again, I'm not going to do a fair representation here of what happened, but it took more than 4, now perhaps 5 decades for numerical relativists to really solve the binary black hole problems. There were a lot of instabilities in the early formulation of the Einstein equations. We didn't know how to set up the gauge. And then we had a curvature singularity. And I really like this writing from the first, and this was from a proceeding of the first GR1 conference done by Charles Misner. And you can see how in this very first conference, so you see that this is dated actually 1957, right? And he had somehow predicted the difficulty, okay? Then we solved the problem. The code didn't blow up anymore. This happened with Franz Pretorius in 2005 first, and then the following moving puncture approach that was developed by the NASA Goddard and my own group back in 2006. And the codes didn't really started to work, and this big elephant that you see leave the room. So a lot has been done in solving the Einstein equation, but what has been done in solving other type of equation? One can think about that there could be modification to GR, and that right now we're not able to resolve with the current detector. But if there are modifications, then we need to be able to model those. And there has been quite a bit of work in proof of principle simulation in beyond GR theory in the past, mostly focused on perturbation theory and work around single black hole and neutron star. But recently, there's been much more work in really modeling compact binary, both in the post-Newtonian theory, but also in numerical relativity. And I mentioned here just a few of them and the various models that have been done. So this is now also present in the Einstein Toolkit, the Canuda approach. I hope that Helby is going to say something here. So this is really exciting because one can start exploring this theory. The motivation behind this theory is usually because there are low energy limit of string theory or quantum gravity or that contains small deviation from GR. The big elephant in the room is how we need to really model more of those. There are many of these theory, and we need to be able to distinguish non-GR correction from, for example, numerical relativity error. Okay. So I'm going to speak a little bit now about next generation numerical relativity code. As you recall, in one of my slides, I had many of these codes listed. A few of them, though, can be brought into the category of next generation code. Those are codes that are really promising in terms of enabling scaling into millions of core for exascale computers. And I'm listing some of them here: SPEC and Spectre and Mesh, Dendro GR, GR Athena++, BAMS, and GR Chombo. And of course, the Einstein Toolkit, call it X codes, the future of the Einstein Toolkit. Many of these codes use some of these techniques. Not all of these techniques are used by all these codes, but I'm just listing here some of them. So some of these codes use discontinuous Galerkin methods for exponential accuracy with resolution. Okay, discontinuous Galerkin divide the computation domain into more and smaller cells that, so they can communicate only with their nearest neighbor. So they become much more efficient this way. There's task-based parallelism, okay, which minimize global synchronization and load balances, which is really applied in some of these codes. There is also an approach called the wavelet adaptive multi-resolution representation. This is used, for example, in the Dendro GR code. Improved AMR open sources package. We're going to briefly mention about MRX here, but there is going to be a talk by Eric Schneider on the topic. And the use of GPUs, I believe there is a tutorial on Friday on this. And then finally, a topic that is very dear to me, but also to Zach here, is the taking advantage of curvilinear grades. We're going to see how that actually is helping us. So for codes of the exascale computer, we'll first mention Spectre. Spectre use continuous Galerkin metric and task-based parallelization. Here, there are some figures that were provided to me by Niels Deppe for my APS presentation. I don't know if they are the latest update, but updated figures, but they are certainly already fairly impressive. You can see the efficiency for elliptic solvers and as well for the first several orbital binary black hole cloud. So I believe that Geoffrey Lovelace will be talking about both the SPEC and the Spectre code in this conference, and Niels View will be also presenting about the Spectre initial data solver. Okay. So I don't know if there is I didn't see a Dendro GR presentation in this or Athena++ in here. So I will mention those a little bit more. So Dendro GR was a code developed by Fernando in 2019. It's based on an unstructured grid implementation as distributed tree. And it used wavelet, a wavelet representation, and then conventional finite differencing and finite volume numerical. So the code scale it up to the 10 to the 5 core and is being tested for MHD. I'm showing here a nice image. I see something on my screen, by the way, appearing. Do we have a problem with the network? Hello? Okay.
No problem at all. You're
okay.
good.
Okay, so something popped up in the middle of my talk, like having a problem with the connection. Anyway, so let me continue. So hopefully it doesn't go down as I'm speaking. So Giratina++ is another code that is fairly interesting, also using octree MR. And it's also scaling, claims to scale up to 10 to the 5 cores, and also has GRMHD implemented. So these are fairly interesting development. And you can see here how they're fairly new development. You can see here how, for example, some of the code, the waveform comparison has been made between the current codes and future code. Right now, they're under development. Okay, so as this is a school on the Einstein Toolkit, so I'm going to have to mention a little bit about the Einstein Toolkit. Although there will be a tutorial by Roland Hess on the introduction of the Einstein Toolkit. So, and then Josef Zlochover will tell you about how to write a torn in the Einstein Toolkit. The future of the Einstein Toolkit is right now focused on developing CarpetX, what is great part of it, not entirely. CarpetX is a new driver that is for adaptive mesh refinement, which is based on the MRX framework. The MRX framework is a DOE funded project that was developed by a number of people here, which I mentioned on a slide. It's available on GitHub, and it's providing a set of libraries and also just for more efficient EMR. But also it's providing the ability to do GPU calculation, for example. So I think Eric Schneider will be talking about this topic on CarpetX, and Steve Brandt will also give a tutorial in relation to Carpet and CarpetX torn using RP. And so this is fairly exciting because it will allow the Einstein Toolkit to enter into the classification of the next generation type of codes where you're able to do much more efficient and accurate simulations. So in fact, we'll also start working fairly soon on applying CarpetX into the domain of GRMHD. There is some initiative that some of the postdocs and students in various groups are working on. I'm mentioning here, there will be a GPU tutorial on the Einstein Toolkit, which will use some of the techniques that will be developed also in the context of this new GRMHD code that now I understand is being called AsterX. So again, you'll hear a lot about that. Okay, so this is about making numerical activity open and affordable. This is actually, I think, what Zach has and Leo have been championing a lot. The NeRP code is really used widely now for code generation in the full numerical activity domain. It's really an efficient Python-based code that generates C code. So you're not making, you're reducing a lot your ability to make errors to write codes if you use NeRP+. And there is going to be a talk about this describe how actually this NeRP plus can be also used to improve not just numerical activity, but also the performance of other, for example, analytical relativity and numerical activity hybrid methods. Finally, I would say it's been applied to generate code. Obviously, Illinois GRMHD is being the example, supreme example how NeRP can generate efficient codes. Illinois GRMHD, as you know, is a open source code, is part of the Einstein Toolkit, use now tabulated equational state, neutrino leakage, and has many usable diagnostic particle tracer, volume integral, etc., and contains some handoff routines. Leo Werneck will give you an update on the Illinois GRMHD code, so I'm not going to say much more here. And finally, the idea that one day can do black hole simulation on desktop. This is something that Zach Etienne will be talking about with the Black Hole at Home initiative, and as well as this code, Curvilinear, that is using efficient curvilinear grid structure in order to, with the goal to generate a very large accurate gravitational wave catalog very efficiently. I'll tell you a little bit more about curvilinear coordinate later, but this I think is a very exciting development. Okay, so finally, I also want to mention here about the need of doing more code comparisons in this field. Because, well, especially in the case of binary neutron stars, we are discovering that we need to do better in comparing the output of these codes. This is an example done by Lorenzo Enocci, where he compared the results from the Illinois GRMHD and Spitz code. And as you can see, we need to really get to understand some of the differences that we obtain, not just because in the binary neutron star case, the black hole remnant might form later or earlier. The merger time is different, but also before actually the merger happened, we are noticing that there are some differences, both in the waveform calculation, but also in other quantities. So this needs to be really looked on, and I really encourage this community to start thinking about doing more comparison, especially in the case where there is matter. Okay. So, and I'm going to address some other questions here about binary neutron star simulation and whether long-term simulations are possible. These are very challenging simulations, as you know, but they're very important because they are at the core of multi-messenger astronomy. For binary neutron star, we want to know some key questions like what is the central engine of a gamma ray burst, what is the nature of the remnant, what is the equational state, and how the jet is launched, magnetic field amplification topology, how much mass is ejected from the system, if there are neutrinos, what role neutrino plays, and how this is all associated with the kilonova signal. So we have a lot to really go after with binary neutron star system, but it's extremely challenging, and it does require that we do very long simulation the post-merger or the post-merger phase. Unfortunately, this requires not just numerical activity, but also GRMHD, nuclear and neutrino physics, the treatment of equational state, various equational state, often tabulated equational state from nuclear physics, and neutrino and phototransport, and our process and nucleosynthesis. It's really an inherently multi-physical and multi-scale problem. The resolution to really nail down the physics here is incredible. So we have to resolve the scale of the magnetorotational instability, not just the scale of the gravitational wave, which is larger. So here's one of the outstanding simulations you see on the screen from Kiyuki, and it was done now a number of years ago, and it remains really an outstanding simulation. It has been done using an amazing number of cores and resources that unfortunately are not available to everyone to be able to make progress in this field. So we have to do better in the modeling. So
Manuela, just to interject, you have 5 minutes before we'll have to move on to the next speaker.
Oh, I'm sorry. Okay, let me get it. Thank you. So we need to simulate more than 1 second, and in order to do this type of simulations and be able to predict the electromagnetic signals, and let's say we need to get to the scale of the MRI. So let me just mention briefly here what we are doing in trying to do this. We have to, the way we're doing it, we divide the problem according to the physical characteristics, and then we can use different codes and grids for different regime, and developed then self-consistent techniques to hand off the results from one code to another. So let me just move on. Okay. I think this is, I think, well, I'm not sure if Leo will present it, but I think he might present this, where we do a handoff from a binary neutron star simulation using Illinois GMHD to its code using spherical coordinates. And you can see in this simulation that this can be done. It's fairly, the actual handoff techniques are fairly complex, but it can be done in a reliable way. And you can see that through this, you can continue the simulation and continue it for quite a long time using spherical coordinates, which are more efficient and accurate in the post-merger region. So let me just move on. I think I'm going to skip on this, but it's, there are some interesting new results on their way using these techniques, where we can find interesting results. For example, in this plot, you can see the magnetization increasing after some times in the post-merger, and we are looking at finding new results about this soon. So curvilinear coordinates, I want to say something about curvilinear coordinates and why they're important. They're important because they're widely used, first of all, in astrophysics to treat problems like in black hole accretion. They're obviously very good to treat for angular momentum transport because the flows are in line with the cell boundaries. They're also very good to do post-merger or binary neutron stars. Okay, there is this various codes that use spherical coordinates. One of the codes I want to mention here is spherical NR, is built on top of the Einstein Toolkit and has GRMHD implemented. I don't have, unfortunately, time to go in all the details, but some early comparisons of this code have been made with an existing and mature code like HARM3D. This is the accretion rate, for example, from a binary black hole, a circumbinary disk around a binary black hole. And you can see how the HARM3D code and the spherical NR code are going, are essentially in good agreement. So this is a new development, as I said, will be available soon in the Einstein Toolkit for use in numerical activity with spherical coordinates. Okay. So this type of codes can be used to do calculations of accretion, for example, for binary black holes. So this is a problem that requires very long-term simulation. Again, spherical coordinates are much more efficient to deal with this type of problem. So you can see here we're dealing with more than 250 orbits. And so there's no way you can do this without having efficiency and accuracy. Accuracy is needed to resolve the MRI. So I don't have, unfortunately, a lot of time to show you this simulation. So I'm going to go forward quickly. This is to show you one of these handoff strategy. This is now from a spherical code to another almost Cartesian codes to do the merger. And you can see how you can use a strategy to evolve the circumbinary disk for many, many orbits, hundreds of orbits, and then hand off this to a code to do the merger. So unfortunately, I don't have a lot of time, but there is a lot of interesting physics that we've been able to do this way. Okay, and we are discovering quite a bit of rich structure, and by using these techniques in this binary black hole problem, supermassive black hole binary problems. And you can also calculate through this strategy, handoff strategy, you can calculate a number of things, not just gravitational waves, but light curves. For example, you can see here the binary supermassive black holes calculated through these methods. So unfortunately, I have to really get to the conclusion since my time is over. But if you have questions, I'd be happy to talk a little bit more about the things that I had to really rush a little bit toward the end. I just want to say here that we absolutely need to continue to develop our 21st century tools. This involves cutting-edge numerical algorithms, sophisticated software infrastructure, physics, insight, and computational strategy can also, by the way, aid greatly. As I mentioned it, curvilinear coordinates are certainly falling into this category. And finally, if we really want to do multi-messenger astronomy in the near future, then we really need a sustained and community of cyber infrastructure, and we need not just powerful supercomputers, but we need a community. And the Einstein Toolkit has been able to do this. One of the great achievements of the Einstein Toolkit is to indeed have him build a numerical relativity community. Of course, in all of this, we need funding. We'll need continue to, because this is what support the students and the postdocs in this field. So I hope that these type of schools and workshops are going to be really useful to grow the community and to advance this field in order to make the progress we need to do in order to do multi-messenger astronomy, because I think the future looks really bright with all these third generation gravitational wave detectors and LISA going up. There is really a lot that we are going to learn, and numerical relativity has to be there to provide insights about these discoveries. Thank you.